Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresuan University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Okay. Good afternoon, everyone who actually in this room and also watching online. Okay, so welcome to IF Colloquium number 30, I believe. So, today we have a very special guest, which is Adan Thiparat. Chotibut. Okay. Can you hear me?
Yes, very clearly. Can you
Okay.
hear me?
Okay. So, so Adan Tip, okay, he is a lecturer at the physics department, Chulalongkorn University, and also head of Chula Intelligent and Complex System Research Unit. So, okay. So today he's going to tell us about localization links in random current neural networks. Okay. If you're ready, please. Okay. All right.
Okay. Let me try to share my screen quickly. Okay, I probably have to quit and come back again because I need to set up some screen sharing.
Right. Okay.
I'll be back in 30 seconds.
Okay.
Okay. Can you guys see my slides?
Not really yet. Okay, it's coming now. Okay, we can see it now.
Okay, you can see the slide. All right.
Yeah.
Sorry for the inconvenience. Thank you, Janrin, for the invitation and also for the opportunity to give this talk and a nice brief introduction. So today I'll be sharing my recent works concerning the ideas of randomness in recurrent neural networks. There'll be two aspects of the talk. The first aspect is more connected to computational neuroscience results, where experimentalists have recently found that mice trained with a noisy brain, there's noise in the signals, in the activities in the brain, turns out to have a better performance in terms of working memory performance, which I'll explain to you what working memory computation is. This phenomena is quite puzzling from the standpoint of learning, because one knows that noise typically can destroy information processing capability. But in this case, in neuroscience, some phenomena such as working memory has been shown that noise can enhance capability to make computation. And I'll tell you a specific model of recurrent neural networks when ejected noise find the same phenomena in which noise can enhance information processing capability for this kind of task. And I'll try to explain the mechanism that we found and also pose some open questions that could be of interest to statistical physicists. And in the second part of the talk, I'll be talking about a specific type of ring recurrent neural networks model. That is a prototypical linearized dynamics leads to the Hamiltonian that looks kind of like picture on the lower right here. That resembles type binding models with nearest neighbor hopping, but there'll be a directionality bias that enables the model to prefer one direction of information propagation rather than the other. And by breaking this hermiticity in the standard type binding model, coupled with the on-site disorder, there could be interesting competition between on-site disorder, which leads to Anderson localization, and the directional bias, which leads to delocalization phenomena. And I'll tell you that in this specific case of neural networks model, studying the eigenstates of it allows you to look into neural response in the simple model, and more importantly, the localization and delocalization transition of the eigenstates. I'll try to argue that it belongs to the topological phase transition. So there'll be two parts of the talk. And I'd like to acknowledge my collaborators. In the first part of the talk, in collaboration with Professor Natida and Terry Sanowski, and also Dr. Robert Kim. They are mostly neuroscientists, machine learning scientists, and a real psychology doctor. And in the second part of the talk, it's done locally in collaboration with my fourth-year undergrad student, Chulalongkorn, who's leading the calculation in the work, and also an expert on topology, Dr. Napat, who is another faculty member at Chula here. All right, as I alluded to earlier, I'll be talking about two aspects of recurrent neural networks. In both cases, the important structure mathematical object that we will study is the localization length of the eigenfunction, which I'll explain eigenfunction of what. Okay, and the first part of the talk, the paper is under revision and hopefully it will appear soon in PNAS. All right, so let me tell you about a biologically plausible recurrent neural network model. Many of you probably have heard about recurrent neural networks model many times because it's the backbone of modern temporal machine learning algorithm, including language model in the early days before large language model was developed. So in recurrent neural networks model, you have a bunch of neurons connecting with each other, and each neuron can also pass information to itself. That's why it's recurrent. But a biologically plausible RNN, there's another feature that came into the picture, which is each neuron can be in only inhibitory states or excitatory states. This is the so-called Dale's principle. The inhibitory neurons, we only send out the negative signals to the neuron that are connected through the synaptic way, Wij. So if a neuron J is an inhibitory neurons, all the Wij for all I will be negative, which means that it sends out only the negative signal. But if the neuron is excitatory, then the connectivity that came out of that particular neuron will be positive. So if a neuron J is excitatory neuron, Wij will be positive for OI. And this is kind of well documented experimental facts that neuron in their lifetime can only be in one of the two, but not neither at the same time. Okay, so the typical dynamical system that describe the so-called firing rate recurrent neural networks model is the following equation that you're seeing. So each neuron eye will relax to the steady state without any external input from other neurons. So if you look at only the first term on the right-hand side, that's the relaxation of the activity of each neuron eye. And tau I is the characteristic synaptic decay time constant, which sets the characteristic time scale in which each neuron relaxes or progresses over time. And the middle term on the right-hand side tells you about the aggregation of signals that come from other neurons that are connected with neuron I. And Wij can have a non-zero diagonal elements, which means that the model is recurrent because you pass information from the same unit to the same unit in the future. And the last term is typically whatever comes into your neural networks, such as external input or some other sensory information that part of the recurrent neural network is exposed to. And that could be UV channel of those. And the function R, I haven't told you, it's the activation function. In this case, I'll use the biologically plausible one, a sigmoid activation function. Sigmoid of x is 1 over 1 plus exponential to the minus x. So if the activity x is minus infinity, then the activation function or the activity R, excuse me, will be close to 1 or to 0. But if the activity, sorry, if the activity x is infinity really large, then R will be close to 1. Okay, so if x has no activity at all, it's extremely negative value, then the activation function that will propagate to the next unit will be 0. But if x has a high activity, then you can think of it as a kind of a switch that turn on the signal and get activated and pass on to other units. All right, I would like to highlight in the standard models of RNN that people look into. This is called a firing rate leaky integrated fire model. People typically neglected this variability in the synaptic decay time constant tau I. They typically assume that tau I is homogeneous for all the neurons I. However, in experiments, which I also discussed in a little bit, just want to highlight now is that there's some variability in the real neuronal dynamics in which they found that the rat brains that are exposed to more noise turns out to have a specific inhibitory unit's decay time constant to be longer than those of the time constant of the excitatory units. That's the experimental observation. Okay, then the question becomes, well, now I have explained to you what are the dynamical system simplest model to explain biologically plausible RNN models consisting of inhibitory unit and excitatory units. What can this RNN do in machine learning or in actual learning tasks in neuroscience? You can train this RNN to perform certain tasks. And a typical task would be you have some input function and you read out some activities of this RNN and ask it to perform certain output. So it's a kind of high-dimensional mapping between input functions and an output functions. And the output function is some output vector O as a function of time t that is computed in certain way by a function f. And by training, I mean that we can adjust the weight Wij of the neural network's architecture itself. We can adjust the synaptic decay time constant tau I, and also adjust the function f and a W out. All right, for specific tasks that I'd like to focus on is working memory task. This is the so-called task called one delay DMS, delay match to sample. The idea is that you input time series signal consisting of a boxcar signal with two possible signs. either +1 sign or -1 sign. So there'll be 4 combinations of this boxcar. After the first stimuli hit, there'll be some delay period. In this case, I show it to be 250 millisecond delay period, followed by the second stimuli, which can be in either +1 or -1. The goal of this task, DMS task, is to train an RNN such that it distinguishes whether the 2 boxcar signal with certain delay time period share the same sign or opposite sign. If the 2 stimuli have the same sign, then you ask the RNN to output +1, that sign match. If the 2 input signals have opposite sign, then you ask RNN to output -1. This will be our training task, which is also used as some sort of a proxy when you train mice as well. Okay, and then you can think about increasing the delay time period and imagine why this is a good task for testing the so-called short-term or working memory computation, because you need to memorize what is the sign of the first stimuli after the delay period has passed, and then try to match whether the long past stimulus match that sign of the second stimulus, right? So the task will be harder as you increase longer delay time period. Anyway, so if you guys have any question, feel free to ask right away, because there'll be a lot of subtleties, and I know this is not common knowledge in theoretical physics, but if you let it pass, and you probably won't know what's going on later on in the talk. So I would like to encourage you to interrupt me anytime, and also I'll feel much more like talking to people rather than talking to myself. Okay, so this will be the task, and the task will be simple, just the output the sign after the second stimulus has passed, and check whether the 2 stimuli that comes into a 2 boxcar has the same or opposite sign. Okay, and the task will be harder as one increase the delay time period. I hope this is clear. All right, so training in this case will be, we just perform usual regression. The output will be some linear matrix W, in this case a vector, that dot products with the current activities of the neurons in the neural network at the current time, and B will be just a scalar parameter that can be used to fit the model. All right, and there'll be some training parameters. Rather than just train with the usual backpropagation, train just changes the RNN weight architecture Wij, and also train the regression W out weight. In this case, I would like to highlight that tau I, which is the synaptic decay time constant of each neuron, will also be trained. This is the key distinction that other works haven't looked at before. All right, and why do I want to train tau I? Because as I alluded to earlier, there are findings in experimental neuroscience that found that mice with better working memory, when they are exposed to a noisy signal, inhibitory units will have a longer delay time constant tau I. And we'll see whether or not these simple models can reproduce results that is found in the lab. And also I'd like to mention that the excitatory to inhibitory unit ratio will follow what's biologically possible. In this case, we set it to be 80% to 20%, and this ratio will be fixed. So namely, only the weight motive of the RNN will be trained, but the type of the neuron, either I or E, will be fixed. All right, in order to reproduce the result or try to see whether or not this is a good model and whether noise can enhance computation, we would like to inject noise into this collinear dynamics. So the noise will be injected in the following linear weight way. Wij will be random. The Wij noise will be random, and psi j in each channel from the first channel to the C channel are taken to be a Gaussian white noise, uncorrelated in time, with the variance to be delta square of phi. And it's uncorrelated between each channel as well. That's why it's written as a correlation function below the red box there. And many of the mathematically trained people would have already figured out that, in fact, this is the sum of Gaussian random variables. So in the end, this is just another Gaussian random variable with a rescaled mean and variance. In this case, I would actually take the mean to be 0. So the mean of the new random variable will be 0, but the variance has to be rescaled appropriately. But I would like to write it in this way because it's how experimental neuroscience think about sensory noise that could be multiple channel, uncorrelated with each other, interacting with your RNN substrate. Okay, so let's see the task when we inject noise into the computation. Of course, we first need to train the model. So we look at the training success rate. And this is not a surprising result for those of you who know regularization and stochastic gradient descent in machine learning. As you can see here, as you increases the number of noise channels, or equivalently, you can say you increases the noise strength in the Gaussian white noise rescaled mean, the training success become larger and larger. That 0 number of noise, so in the noiseless case, the training success rate is roughly about 65%. Success rate is computed from you train this on 20,000 trials, and then if the success of the training accuracy exceeds 95%, we will say that that training trial is successful. And as you increase the number of noise channel or the noise amplitude, the training success increases. I said it's not surprising because it's a well-known fact that training with noise has some regularization effect. So training becomes easier. This is heuristically known in some models, not specifically to temporal machine learning models that I'm talking about. However, the other aspect of noise allowing you to escape local minima is kind of well known. So this could be attributed to that fact. Suppose you are training, the cost function has a very rugged landscape. By adding a little bit of noise allows you to perform backpropagation with noise that kick you out of the local minima, and that's why you can reach a higher training accuracy with the help of noise. But that's not very surprising. Of course, you cannot have an infinite noise, otherwise everything become a mess. And then, of course, this statement is true when you have a moderate noise strength, not infinite noise, of course. All right, so after we have trained successfully this neural networks model, we would like to now remember that we have the delay time period that can be adjusted. We know from experiments that increasing the delay time period becomes harder for the mice to perform this task because it already forgets its past. And what we are seeing here is that models trained with more noise channels turned out to perform better in terms of the accuracy and the test performance in unseen input signal that is noisy. You can increase the delay time constant, the delay time period between the two boxcar, and found that the larger the number of noise channels, the models can predict better. So in this case, it's kind of consistent with what experimental neuroscience found in the lab. So noise enhance the simple biologically plausible RNN computation to remember the past better in order to make decision correctly. All right, so of course, as a physicist, we would like to understand what's going on. We do not just want to reproduce statistical result without looking into the inner working of what's the mechanism behind this noise-enhancing memory computation. So I'll look into different activity patterns of the neural trajectories. In the past, I have shown you statistics of models with 200 neurons. So if you look at the dynamics of neural networks, it looks something like this. And the color in the log scale show the activity of each neuron that appears as an index on the vertical axis. And these are shown for neurons trained with noise, and is shown as an activity during the delay time period of 250 milliseconds. As you can see, it kind of doesn't change color much, which means that these might suggest that the neural activities during delay time windows has reached some sort of dynamical steady state. Okay, so what does the steady state look like, right? So between with noise and without noise. In fact, I would like to ask, how does the whole neural trajectory look like in the 4 different input stimuli condition, which are colored differently, as shown on the left here. All right. So if you look at the output first, rather than looking at the activity, you read out and then make this scalar computation of whether to predict +1 or -1. As you see, after the second stimulus arises, in both model trained with and with large noise, in this case moderate noise, and weak noise, they all go into the right direction. For example, the color black, which shows that the 2 signs of the stimulus are minus match, they should go to +1. They actually go to +1 because these are successfully trained model. And in case of the opposite sign, such as purple color, after 1000 millisecond pass, the model output -1, which is what we expect. However, if you look at the amplitude of fluctuations, if you don't look at the label of whether it's a weak noise or the moderate noise, I would have guessed the opposite. That is, the left figure should appear to be a more noisy input, should be more susceptible to larger noise. And on the right, it should be less susceptible to noise if you just visually look at the fluctuations. But it turns out not to be the case because these are the trained neurons. In the left case, we have a smaller number of noise channels. However, models trained with a stronger noise have an output that is less sensitive to noise, as shown on the right. And interestingly, if you look at not just the output, but look at the representation or the neural activities of those 200 neurons, in this case, I use a dimensionality reduction techniques to visualize 200 dimensions faithfully in 3 dimensions using a technique called FATE. People in bioinformatics use it a lot. It's a way to compactly compress information about 200 dimensional vector into 3 in such a way that the distance between the 2 points in 200 dimension is roughly preserved to the distance between 3 dimensions that you are seeing here. So as you can see, model trained with a stronger noise turns out to have a representation of neural activities that are more refined compared to the model trained with weaker noise, which seems to be much less refined in terms of a neural trajectories. This is quite surprising. All right, another observation fact that we found that is consistent with experimental neuroscience results in mice is that models that are trained with stronger noise turns out to have inhibitory units, specifically, not excitatory units, synaptic decay time constant to be larger. So this is in agreement with what neuroscience in the lab found. If you look at the activities of the slower inhibitory units or the slower relaxation dynamics, we find that the average activities for the models trained with the stronger noise of these units turns out to have a longer tail in terms of decaying after the first stimulus hit it, which potentially tells us that there is some memory of the first stimulus that remains longer before the second stimulus hits in order to make decision, before it makes decision. So this is so far so good, consistent with what we found in the lab, and then kind of intuitively makes sense because these slower decaying units hold information in the past longer. All right, so now we would like to ask specifically what's going on, right? We have these clues. Can we understand better in terms of relaxation dynamics? One observation I told you earlier is that during the delay time period between the first and the second stimulus, what we found is that it appears that the neural activities remain relatively stable. Okay, once the neural activities remain relatively stable, we can calculate an average steady state patterns. In this case, I'll call it X star of S1. S1 is the first stimulus. So depending on the first stimulus, whether it's plus sign or minus sign, this neural activity will be different, as you can see on the left and the right, respectively. Okay, now once you have the steady states, one common tool in analyzing the response and the susceptibility to noise or perturbation is to do the so-called linear stability analysis, which basically asks you what does the linearized dynamics around the steady state look like if you perturb it by a little bit. In this case, the perturbation delta of x s1, delta of x s1 is a small perturbation of the steady state, will evolve in a short time according to this linear equation. And the eigenvalues and eigenvectors of this linear equation will tell you how the response delta x or the perturbation delta x grow or decay over time. And the eigenfunction structure will tell you about the sensitivity to perturbation and how much of the neurons participate in the response. And Jij here is computed from the full linearization of the nonlinear dynamics I told you earlier when you average out the noise. Okay, so in this case, Jij will be non-symmetric because after you train the model, you find Wij to be highly non-symmetric. And sigma here, remember, is a sigmoid activation function, so the value is between 0 and 1. Okay. So how does this perturbation lead to the response? And how does the structure of this Jacobian Jij going to tell me about the steady state that arises from models trained with and without noise? It has to do with finding spectral decomposition of this Hessian matrix Jacobian Jij. So if you look at the spectral decomposition of Jij and plug it in to the first equation, what you can see in the equation in the box is that it's saying that if you have the initial perturbation of delta x at time 0, this initial perturbation will interact with the left eigenvector of the matrix J, and that will lead to the response structure. The activity of neuron response will be determined by the right eigenfunction psi of r. And the rate at which the response grow or decay will depend on the real part of the eigenvalue lambda of n. And then you sum it up, all of the perturbation and response together to get the full response of the initial perturbation, delta x0. So if your eigenvalues of Jij has all negative real parts, it means that any perturbation is stable. It will eventually relaxes to the steady state. But if some of the eigenvalue is positive, it means that that particular perturbation is unstable, and it can cause your model to deviate from the steady state, and that's not what we want because we observe the steady state is reached. So how do we quantify whether or not the model is more or less sensitive to perturbation? So that depends on the amount of neuron participating in the left eigenvector. And one metric to compute and quantify that is the inverse participation ratio, which is highly used in localization phenomena in statistical physics, for example, in Anderson localization, in condensed matter physics as well. So this inverse participation ratio tells you how much neuron needs to be participated in order to, if you look at the left eigenfunction and compute the inverse participation ratio of the left eigenfunction, it tells you how many neurons you need to perturb in order to lead to the response. So if your IPR is large, in this case, the maximum value is 1, it means that you only need to perturb only one neuron, and then the model will lead to the response in the neural dynamics. The minimum value of IPR, in this case, is 1 over n, where n is the number of neurons in your system. So if IPR is the minimum at 1 over n, then you need to perturb most of the neuron, all of the neuron, and then that will contribute to the response. So model with smaller IPR will be larger to be perturbed, and model with smaller IPR, larger IPR left, closer to 1, will be less, we will be more prone to perturbation. We will be more sensitive to perturbation. So that's the key point that you probably have to remember, which will appear again in the second talk as well. All right, so we'll look into models trained with weak and the moderate noise and see whether or not model trained with the stronger noise is less prone to perturbation. In other words, is it going to have a smaller IPR? All right, so I'm showing you here the eigenvalue distribution and plot as a color the log scale of the inverse participation ratio of the left eigenfunction, because we want to look at how sensitive to perturbation the models are. Remember, if the color is close to 0, in this case, IPR left is close to 1, perturbation can be localized on only some unit and it leads to large response, which means that model is more sensitive. If IPR has a green color, it's close to the delocalized state. It means that that particular left eigenfunction requires a lot of neurons to be perturbed in order to lead to response. So it's less prone to perturbation. So as you can see, model trained with moderate noise, interestingly, eigenvalues, most of the eigenvalues that has a complex components shift towards 0. Remember, the real part of the spectral tells you whether the model is stable or unstable. In this case, the real part are all negative, which is consistent with what we told you earlier, that is a steady state. So the model is still steady, but the distance from 0 tells you how fast things relax to equilibrium. If the real part is really close to 0, it means that it's stable, it's relaxing, but with the rate that is very, very slow. It takes a long time before the signal that you perturb relax to steady state again. So as you can see, in the moderate noise case, the eigenvalues spectrum shift closer to the right, which means that the models will relax much slower than models trained with big noise. This is consistent with the plot that I show you here, where the tail after the first stimuli hit of the models trained with moderate noise relax slower. So the information of the first stimulus still remains. Okay, now if you look at the IPR, we can see also that the slower modes, the modes that are responsible for holding memory of model trained with moderate noise, turns out to be very delocalized. Most green colors on the right of the spectrum. As opposed to the model trained with weak noise, there are some purple color or localized spectrum that are slow, which means that even though those are slow modes, it's very sensitive to perturbation, as opposed to models trained with moderate noise. Right, so this kind of agrees with the observation I told you earlier in terms of remember the past. We want the information of the past to remain, yet you still want to be in the steady state. So you have to be in the relaxation or dissipative phase, which means the real part has to be negative. But the real part has to be negative in such a way that is not too negative, otherwise information relaxes too fast. And as a result, you have to be close to the so-called the edge of instability, which is shown in the vertical pink color dashed line here, where the eigenvalues, the real part is 0. If the real part becomes positive, then you get into a chaotic phase, and then information that comes in or any noise that comes in will mix up the states of the RNN and becomes useless in terms of making prediction. So as a result, what we found is that not only the inhibitory unit's time constant increases, model trained with moderate noise lie at the edge of instability closer to the stable side of the phase. And the edge of instability helps you in terms of remember the past longer because the relaxation dynamics is lower. And also, interestingly, the sensitivity to perturbation of model trained with stronger noise is less sensitive compared to model trained with weak noise, as can be seen in the IPR plot. Okay, so some people might have thought, well, is this true for on only working memory computation tasks, or is it true in general? So we applied this training mechanism with noise and without noise in the task that doesn't require you to hold memory of the past in two tasks specifically. The first one is to check whether there's a stimulus that comes in, and then you don't care about what happened in the past. You just check whether there's stimulus. If there's stimulus, then you output 1, and if not, you output 0. The other task is to distinguish the two context signals. There are two input modalities. Each of the modalities have different patterns. You don't need to require to memorize the past. You just need to distinguish whether the two modalities are different. These two tasks, you do not need to remember the past. And what you can see on the right is that the inhibitory unit time constant doesn't depend on the number of noise channels. So noise increase in inhibitory unit time constant is specific to working memory computation. All right, so I'm going to summarize the first part of the talk for the interest of time. So we found that training biologically plausible RNNs, according to the Dale's principle with moderate noise, surprisingly, and in agreement with experimental neuroscience, that it leads to a more stable working memory maintenance, right? People in the past might have thought that noise destroys information processing, but in this case, in this particular model, the model is trained and evolved to harness noise to perform useful computation. And how does it perform working memory computation? It appears that inhibitory unit time constant plays a crucial role. The inhibitory unit time constant increases, and by that increases, it correlates with the fact that there's a slow relaxation dynamics that maintain the information for the first stimulus. And at the same time, it leads to the network motif that is less sensitive to perturbation by noise. That's why you see the information representation in this particular case to be more refined when you train model with moderate noise. And of course, this specific task seems, this specific finding is specific to working memory tasks. When you apply to models that doesn't require you to hold information in the past, you don't find these results. All right, before I switch gear to the second part of the talk, is there any question?
Okay, can I ask? That's a very simple question. If I understand correctly, so you consider so far only a weak noise and a moderate one, right? Is it possible to inject a strong noise into your system and then see?
Right. Right. So that, in fact, what I show here is that
All right.
you increase to 10 noise channels, and it works best at 10 noise channels. We increase to 15, the performance drop. Of course, you can imagine if you have 100 noise channels, then dynamics become too noisy and there's no remaining signal. In that limit, it will be useless. So there'll be some sweet spot in which you can ask about how to optimize for the noise channel. But 10 seems to be good enough to observe this kind of noise-enhanced computation.
Okay, that is the reason why you only consider these two cases, right? Okay.
Right. Above 15, the performance drop already, and it's as expected. The noise is too strong, and there's no sensory information that is useful in there anymore.
Can I ask more? One more
Sure.
About at the beginning of your talk, when you formulate here the equation that you said here, here. So you have this dynamical system, right? Here for and your dynamics of your system. do you have any motivation behind to get this kind of equation out of?
Yes. So for a few neuron cases, in fact, for a single neuron, people know that this particular model with noise is what's going on in a single neuron level. In a few neuron levels, people also found that this equation is correct. This is the if you look into standard textbook theoretical neuroscience, they call this model leaky integrate fire models, and it's the backbone of how single neuron or few neurons work. And now you can ask if you combine them into a network, which has the basic ground from real how each and few neurons work. You build into a larger network. What is the computational capability of it? So this is kind of like hydrogen atom of neural network. It's kind of true at a single atom level.
I see. Okay. Any further question? So I think no. Okay, you can continue for your second part, please.
Okay, so in the first part, this Jij comes out from training. Wij comes from training. So the structure is less amenable to analytical calculation because there's no much structure that we can make any prediction based on the few parameter tuning. But in the second part, also we study this kind of object. But as in a specific model of neural network that has a very structured connection. This is the so-called Amir-Hatano-Nelson model of random asymmetric ring recurrent neural networks. And in this model, you can think of it as the nearest neighbor neuron rather than have a long range synaptic connectivity defined by the graph. In this case, each neuron will interact with only two neighbors, just like in the electron tight binding model when hopping is only to the nearest neighbor in 1D. In fact, that's the motivation. And then there's another term, which is the recurrent connection weight. In this case, it's D of M. D of M tells you the recurrent connectivity will be random. Now you can start to ask if you have this non-symmetric hopping between left and right by adding e to the g terms and e to the minus g in the opposite direction, and increasing g will increase this directionality bias. There could be the competition between the localization. For those of you who know Anderson localization, you know this is the tight binding model of electron hopping on the disordered potential when you take g equals 0 and s to be some sort of rescale momenta. So dm is random, so there could be localization. In 1D, we know that all the eigenstates will be localized. But if you add this asymmetry, which also has some motivation from neural network that is more biased in one direction than the other, this is called ring recurrent neural networks, you break this symmetry, and you can imagine it in a large G in a strong asymmetric hopping limit, you could get delocalization eigenfunction because you can recirculate throughout the whole ring in the periodic boundary condition. So there could be competition between the on-site localization of Anderson type and delocalization due to asymmetric hopping. And people have thought about the phase transition between localization and delocalization transition, but they haven't thought too much about the nature of such transition. And here I would like to argue that, in fact, it is a topological phase transition, which I'll explain in a bit what it means. Okay, so let me describe the model quickly again in a tight binding model language after you linearize the dynamics. S here is the sign of the of each neuron. It's either inhibitory or excitatory. You can tune the ratio of excitatory to inhibitory to be F. If excitatory probability is F, then probability of being in inhibitory is 1 minus F. But for in this particular talk, I'll just focus in case when F is only a half. So there will be equal number of excitatory and inhibitory units. Okay, and the recurrent connection is the diagonal term, dm, and the amplitude or the strength is epsilon. Dm will be a random sign model. SM is also random sign as well. But because of the Thales principle, each neuron output weight can be of only one sign. Once you pick that randomness, then you quench it forever. Okay, so there are some dynamics that could arise, very similar to the earlier models of leaky integrated fire. In the simplest case, when the synaptic decay time constant is homogeneous, this is the nonlinear dynamics that could be generated from this symmetric ring neuron networks. And if I don't care about the bias term, you can play the same game and ask what are the activity patterns when you perturb the model around some steady state. And as a result, you need to analyze this spectral characteristics. And because the model is non-symmetric when G is not 0, this H is non-Hermitian. And as a result, as we did before, we distinguish between the left and the right eigenvectors, which in general are not the same. Okay, so we'll look into the spectrum of these matrices, and because H is structure, the model can be studied more analytically. All right, so these are some known results that came out in 2016 and 19 by Amir-Hatano-Nelson and David Nielsen. So they look at some spectral distribution as well as the inverse participation ratio of each eigenfunction. I'm not sure if the left or the right thing is the right eigenfunction in this case. So red colors mean large IPR and blue colors is small IPR, more delocalized. So in the limit, when there's no hopping bias, G equal to 0, and there's no also on-site disorder, this is symmetric hopping in both ways, but it's assigned random because of the Thales principle. In that case, you get a beautiful spectral curve that looks like a fractal, as shown on the top right here. And the distribution of this fractal now is kind of well known. How is it described? Using some methods of recursive iteration. And if you increase slight asymmetry by increasing G, then there will be a hole around the origin that is developed. And this hole will expand larger and larger as you increase larger and larger G. And there's some known results about the spectral correlation near the origin in the limit of small g. For example, as shown on the lower left here, those are the radial correlation function, which shows that the spectral characteristic near the origin behaves like a liquid, in a sense that the correlation functions has some decay values and it has some repulsion, just like real liquid when it cannot get too close together. So there are some results on eigenvalue repulsion in this non-Hermitian spectra near the origin in the small g limit. A lot of stuff can be asked about how do you discuss this curve, what are the localization length of the eigenvalue function, and so on. Okay, but the limit that is rarely explored, even though numerically observed and studied, is the limit when the hopping is strong, a large G limit. In this case, you can rescale the effective on-site disorder by e to the minus G, and then the effective Hamiltonian in the large G limit will be determined by only effectively one non-random parameter epsilon prime. So if epsilon prime is large, it means that the on-site disorder strength compared to a directional hopping strength is large. If epsilon prime is small, then hopping becomes stronger compared to the on-site disorder. And remember, S plus and DM are sign random model drawn from plus and minus 1 because of the excitatory and the inhibitory character of a neuron. And in this case, it's an equal probability distribution between having the value plus 1 and minus 1. So the chance of that being in plus 1 and minus 1 was a half. Of course, this is written down for n neurons. I haven't added the periodic boundary condition or open boundary condition or even more general boundary condition. Is that If you want to close the ring and make it into a ring, you need to join the first and the last side. In this case, you can join the first and the last side by adding the following term in the box and set W to be 1. But if the first and the last side is not connected, the so-called open boundary condition, then you set it to be 0. And later on, there's another trick that you can add a twisted boundary condition where you have to join the first and the end by some phase factor. And that will come out into play in terms of computing the winding number in the topological field theory. Anyways, so let me tell you about the localization and delocalization of the eigenfunction. As I said earlier, if you understand this physics, it's very simple, right? If you have a really strong hopping limit, meaning that epsilon prime is 0, there's only one way, one directional bias hopping, all the eigenfunctions should be delocalized, because once you're at one point, then you recirculate in the chain and come back to itself. So you necessarily have to visit every single point. And as a result, eigenfunction, if epsilon prime is 0, has to be delocalized. And the spectrum looks like this. It becomes a circle. You could write down the analytic form in that particular limit. Okay, and what I'm showing on the bottom is the amplitude of the eigenfunction. That is the most delocalized. But because in this case, all the eigenfunction, in this case, only the right eigenfunction that we care about, we care about the response. All the eigenfunctions are delocalized, and as a result, all the sites are occupied uniformly with the amplitude of 1/n. If you increase the on-site disorder, of course, in the Anderson localization spirit, you would imagine that there will be some eigenvalues that start to get localized around some strongly localized on-site disorder. And that's actually what you're seeing here. As you increase the on-site disorder, there will be some eigenfunction, in this case on the rightmost case, rightmost of the spectrum, that is the most delocalized. Remember, the larger the IPR, the more localized the eigenfunction becomes. The lower the IPR, the more delocalized or extended, spatially extended the eigenfunction becomes. So the yellow color shows the more localized response function. And what I'm plotting below are two eigenfunctions. One that is the most delocalized, in this case, the one with the real part equal to 0, shown in the blue curve. And the red curve is the most localized one. It localized around some site index 50, 60, 70, something like that. Of course, you can ask, if you increase the on-site disorder, what's going to happen? At epsilon prime is equal to 1, the spectral ring starts to split into a figure-8 picture. And the most localized eigenfunction remains to be the one on the rightmost of the spectrum still. Of course, and then you increase this further, and then you expect localization to happen. Interestingly, if you look at whether or not there exists at least one eigenfunction that is delocalized, you find that when epsilon prime gets above 1, there's no more delocalized eigenfunction. In other words, all eigenfunctions become localized, as you can see on the bottom as well. Even the most delocalized one are still localized, as shown in the blue curves. While at epsilon prime is equal to 1, the most delocalized functions still have the real part to be 0, and that particular one is the delocalized eigenstate. And some of you might have thought, oh, is it related, and conjecture already, is it related to how the spectral topology changes? If you count the winding of the spectrum around 0, whenever epsilon prime is less than 1, there is one winding number of the spectral curve, right? You wind around origin once, and those are the case when there exists at least one delocalized eigenstate. But whenever your spectral ring split into two curves, there's no more winding around origin anymore, and also correspondingly, you don't find any delocalized eigenstate. So does the delocalization transition of the eigenstate has something to do with how the spectral topology change? I'll tell you later. Indeed, it is deeply related. But before going to there, here is another evidence to show that there exists a phase transition. If you look at the minimum inverse participation ratio as an order parameter, the minimum value means that the value is 1 over n, which is shown on the left here when epsilon prime is less than 1. Then there exists at least one eigenfunction with the minimum IPR, so there exists at least one delocalized eigenstate. But whenever epsilon prime increases above 1, even the most delocalized one has the minimum IPR above the minimum value, which means that there's no longer delocalized phase. Things become more and more localized in those cases. Okay, so if we call the existence of delocalized eigenstate as the delocalized phase, and the non-existence of delocalized eigenstates, namely when all eigenfunctions become localized, as a localized phase, then you can distinguish these two phases exactly at epsilon primes equals to 1, which also coincidentally coincide with the fact that the spectral topology changes its winding number around the origin as well. Okay, so let me tell you about how to think about this and how to relate this to observation. But we need to step back a bit and ask about the response function or the Green's function. If you think of the response function as you perturb a system at a site J, and whether or not the system as a whole will have some non-zero response at a site I as some sort of a response function. You might imagine that the eigenfunction might contribute here because you can add the resolution of identity and see that if the response function, Green's function Gij, is non-zero, it means that the right eigenfunction should have a non-zero support on the response side I, right? So you can see that if the model there exists some delocalized right eigenfunction, necessarily it means that the response will be non-zero. Actually, the other way around, sorry. If you imagine that you perturb the system, you hit it with one neuron, and the whole neuron, I, whether or not it's far away or nearby, is non-zero, it means that there must be some non-zero support of some eigenfunction, the right eigenfunction that is there, which means that necessarily there must be some non-zero delocalized. There must exist some delocalized right eigenstate. Okay, so here's how to think about the existence of delocalized eigenstate through the response function or the Green's function. Okay, and you can effectively capture this phenomena by measure the inverse localization length. If your response is of the system size n, and n goes to infinity, which means that there's non-zero response, even though I and j is a system size apart, then kappa, or the inverse localization length, has to be 0. But if the response function is really localized, then it exponentially decay with the system, with the size that is inversely proportional to kappa, right? So whenever kappa is 0, it means that your system respond as a whole, or there is delocalized response function, and necessarily there must exist at least one right eigenstate that is also delocalized. So we can connect the two pictures in terms of the system response of our eigenfunction and whether or not there exists only one delocalized eigenstate that can contribute to the system response, right? So the goal now would be to find a way to compute this inverse localization length, kappa, right? So if we can find a kappa is 0, we know that there exists at least one delocalized eigenstate. And why do we need to care about this system perturbation response formalism? Because it can be in general related to the spectral density of random matrices. So rho of Z is the spectral density at the complex eigenvalue Z, and it's related through the Green's function below. Okay. And remember that this more general response function can be computed for arbitrary C, but what we care about in the argument above to relate it to the right eigenfunction of the system is the statement concerning taking the limit Z equal to 0. So what the strategy that I'll show is that I'll compute this general response function for arbitrary C first, and then eventually take the limit to detect the localized phase in the limit of Z equal to 0 later. Okay, so from the formulation below and the connection between the spectral density and so on and so forth, you can write down analytically the inverse localization length for arbitrary C. And interestingly, this is the contour integral needed to be done for this particular model. It kind of looks like a crying face, and my student Chulalongkorn was really happy to figure out that you can compute this quantity using contour integral with certain branch cut that looks like a bleeding head. Yeah, but you use this kind of contour integral to evaluate the inverse localization length. And what you found is that when Z lies inside any spectral ring, the inverse localization length kappa is exactly 0. All right. But remember, what we care about is to take limit when Z approaches 0, right? Remember this argument. We care about the limit when Z equal to 0. We can compute this inverse localization length for any Z, but the physical one that we can connect to the spectral localization is the one that concerns Z equal to 0, right? So what we see here is that the kappa becomes exactly 0 whenever epsilon prime is less than 1 when Z equal to 0. Now remember, when kappa is 0, it means that the system becomes delocalized. So this is consistent with what we found. However, when epsilon prime is above 1, then kappa no longer is 0, which means that the response function becomes localized. And this is consistent with the observation that I told you earlier. All right, so it seems that the spectral winding number around 0 plays a crucial role. If there's a winding number of 1, it means that the phase of the eigenstate is the delocalized phase. But if the spectral winding number is 0, which happens when epsilon prime exceeds 1, then you're in the localized phase because the spectral winding number is 0. And why is it a deep fact? In fact, it can be shown that this statement about the winding number around 0 has to do with the sensitivity to the changes in the boundary condition. Namely, you can compute kappa in 2 different boundary conditions. One kappa is when you have a periodic boundary condition, which is the standard kappa that I told you earlier. And the other one, kappa sub A. A is some sort of a gauge field that you add. And WA will be the phase that you add a twisted boundary condition to the W term that I told you earlier. If you added the twisted boundary condition and try to match the phase between the first and the last site, then WA is that phase. This is a deep statement because it says that if the winding number or the spectral winding number is 0, it means that you change the boundary condition, the system doesn't feel the boundary condition, and as a result, the 2 response function become the same. The winding number is 0. But if you change the boundary condition and then the response function changes, then it means that the system feel the boundary condition and the winding number becomes non-zero. That exactly happens in our case, because remember, when epsilon prime is less than 1, the winding number is non-zero, which means that if you change the boundary condition from periodic boundary to twist, then the localization length will change. Okay, so this equality is a deep statement that relate topological invariant or the winding number of the spectrum to the boundary condition, and whether or not the response function has a sensitivity to it. If the response function has no sensitivity to the twisted boundary condition or the boundary condition change, then the response has to be localized because it doesn't know anything about the boundary. But if the response function fills a boundary, then it has a sensitivity to the boundary condition. And as a result, the right-hand side, which have the topological invariant, should be non-zero. The winding number is non-zero. Okay. So the result should come out soon. And then for those of you who know Chern-Simon term, the right-hand side is precisely the analog of the Chern-Simon terms that appears in quantum Hall effect. Okay, so in summary, I hope I have convinced you that this phase transition between the eigenfunction localization and delocalization in this particularly simple model can be computed through the spectral winding number changes around the origin, and the spectral winding number changes is a defect that relates the sensitivity to the boundary condition of the response function. Okay, so we are writing up this paper. If you guys want to discuss or have other interesting non-Hermitian model that have this kind of transition, we'll be happy to talk and then try out on a more complicated model as well. But for the interest of time, I would like to thank the audience for the attention, and I'd like to end my talk here. Thank you very much.
Okay. Yeah. Okay. Thank you very much. Okay. Any question? Anyone would like to ask? For the second part again, can we say that actually your second part is just like physics or system realization of your first part? Like you have the first part, you have like a mathematical model, right? In training your system, right? And then your second part, you're talking about some particular physical system, like this kind of bring actually exists, and then it's behave more like the same. If we look at the equation, then can we say that actually this is somehow this realization of, the first part,
Yeah, so if you look at the second equation on the slide here, it's kind of similar to the first part of the talk. But in the first part of the talk, Hij arises from neural networks training. And as a result, there's no clear way to understand analytically as a toy example. If you change certain parameters, how would the neural network respond, and so on and so forth. So David Nelson, my PhD advisor, he wanted to look, in fact, the motivation of non-Hermitian random disorder model. And in neural networks, this is one of the simplest way in which you can have the competition between one-way hopping and also the on-site disorder. So it's one realization of a very simple toy example of neural networks. It's a motivation, it's a neural networks, but in fact, I think people in non-Hermitian random matrices are the one that appreciate this kind of spectral analysis. Yes, I think it would be interesting to extend this simple model beyond nearest neighbor hopping, and you can ask, can you parameterize it to be long range or to be on certain graph structure that has a nice motif that can help you learn noisy dynamics? We still haven't thought about that. That is a big open question, because the question would be, what is a network motif so that it can harness noise that break detailed balance, that use noise as a way to sustain information. So this will be a non-equilibrium thermodynamics project that I'm currently exploring.
Okay, I see. All right. Okay. Thank you very much. Anyone else? If not, then let's thank Ajahn Thiparat again for very interesting talk. Yeah.
Okay. Thank you.
ขอบคุณมากครับ Tip. Okay. So before we go, please tell us help us to complete the survey form, right?
Oh, I see Ajahn Ninnat there.
Yeah, he's here. Okay,
Yeah, I
so
think the thing that is cool about the first part of the project is that we're trying to build quantum algorithm that use noise to perform useful computation, but we haven't figured out how even in classical neural networks, what's the mechanism. So that's the ongoing project. Once we understand that, maybe Ajahn Tom can help me a lot.
okay, then well, then you can actually everyone actually who watching online and also actually on watching online can follow us on the Facebook. Actually, we have all the activity posted up online from the on the Facebook and also from the website of IF. Okay, so if nothing else, then I would like to thank everyone again for today, and then see you next time. Bye. Thank you very much. Bye.
สวัสดีครับ
ขอบคุณครับ